Okay, last time we looked at some examples where we got 0 over 0 as a result of doing our direct substitution. As we're going to see now, that's not always going to be the case. We're not always going to get 0 over 0. Sometimes we get some real number over 0, or what I'm calling here k over 0, all right, where k is not equal to 0. So something like maybe 7 over 0. Okay, in a situation like that, it means that we have a vertical asymptote, or a VA for short, at that x value of interest. Okay. Now, in these limit problems, the overall answer, keep in mind, is going to be either infinity, negative infinity, or does not exist. What you're going to have to do is plug in a value into the function real close to the x value of interest on each side, unless it's just a one-sided limit. And we're going to pay attention to what's happening to y. Now recall that to find the equation of a vertical asymptote, or a VA, you're going to set the denominator equal to 0 and solve for x. Okay, set the denominator equal to 0 and solve for x. Now note that this is different than finding wholes. Wholes are created by common factors. When we have a common factor in a problem, that's when we know there's a hole. But if we're looking to find the location of a vertical asymptote, we're going to set the denominator equal to 0 and solve for x. Okay, let's take a look at an example here. We have a function where x is approaching 2. And notice if we were to perform our direct substitution, we're going to end up getting 7 over 0. So 7 over 0, this is undefined. So note that in this situation, if we were to try to find the location of the vertical asymptote, back up here we said that to find the location of a VA, you're going to set your denominator equal to 0. Well, if I were to set my denominator equal to 0 and solve, we would get x equals 2 for the location of our VA. Okay, so we would have a VA at x equals 2. Now back to the limit question. Trying to find the limit of this function as x approaches 2. So what we're going to need to do here is we're going to have to plug in values really close to 2. Alright, so it's going to look like this. We have the limit. Now let's suppose we call this f of x. We're going to first approach 2 from the left on this function. And we're also going to find the limit of the function as x approaches 2 from the right. So what we're going to do is we're going to plug in values very close to 2. One slightly below and one slightly above. So slightly below 2, we want to use something like x equals 1.99. And likewise over here, let's use something like 2.01. So with our first function here, if I were to plug in 1.99 back into the function where I saw an x, up top I would have some positive number, okay? It'd be 6.99, okay, but it's a modest size number. And in the bottom, if I were to plug in 1.99 and then subtract 2, I'd get negative 0.01. Now keep in mind that I can get closer and closer and closer to 2. I could have used 1.99999. If I had done that, up top I'd still have some positive number, okay, around the size of 7, and I would be dividing it by something that was still negative, but very, very, very small. So in this situation, we would end up with negative infinity if we were to take a positive number and divide it by negative 0.01. Likewise, if we approach our function, if we approach 2 from the right, something like 2.01, if we were to plug that in, in our numerator, we'd see something positive again. In our denominator, we would have positive 0.01. So this time, if we were to look at this, that gives us a result of positive infinity. So if we were to draw this to help us understand what's going on, in this particular case, we said earlier that we would have a VA right here at 2. Well, as I approach 2 from the left, according to what we see here, the limit is negative infinity. So we would have something that's shooting straight down, okay? And as we approach 2 from the right, we have positive infinity, so it would be going straight up. So that means that the overall limit does not exist since the one-sided limits do not match up. So to answer the question here, the overall limit would be DNE because these do not match. Okay. All right, let's move on to a different type of question. Now we're looking at some limit questions where x is approaching either infinity or negative infinity. This means that as x gets real big, in the case of x approaching infinity, or x getting real small, we're trying to figure out what is happening to y. Well, here we're going to follow the rules of horizontal asymptotes if it's a rational function. And we want to look at the most dominant powers. Okay? If it is top heavy, what this means is we actually don't have a horizontal asymptote. And if x were approaching infinity, plug in something like 1,000, something big. Or if x is approaching negative infinity, plug in something like negative 1,000. Now in this situation, your final answer for your limit is either going to be infinity or negative infinity. Now if your powers are equal, your limit is going to be equal to the ratio of the coefficients. And we'll see some examples in a moment. The ratio of the coefficients. And if it's bottom heavy, if there's more weight in the bottom, your limit every single time will just be 0. So let's look at some examples. The first one here, make note that x is approaching infinity. We're only looking at these rules of top heavy, bottom heavy, or equal powers if x is approaching infinity or negative infinity. Okay, so that's a really important point to make. Okay, this is only applicable if x is approaching infinity or negative infinity. So we have a rational function here. If we look up top, the most dominant term, meaning the one with the greatest power, is 2x cubed. In our denominator, the most dominant term is 100x squared. I purposely made these coefficients large to try to trick you. All right. What matters the most is the power of x, not the coefficients. So if we look at 2x cubed versus 100x squared, we want to plug in since, well, first of all, this is top heavy. This 3 right here outweighs the 2. Okay, so the power makes this top heavy. So that means we're going to look at our first situation where there's not going to be a horizontal asymptote. Since x is approaching infinity, we want to plug in something big like 1,000. Well, if I plug 1,000 into this up top, 2 times 1,000 cubed plus 4, all right, is going to be something very large. Okay, this plus 4 is very insignificant. Okay, and likewise down here in the bottom, if I plug in 1,000, these other terms with smaller powers are not going to have as great of an effect as this 100x squared. If I plug in 1,000 there, where I see an x, square it, and then multiply it by 100, you're going to again have something that's very, very large. So overall, our limit here would be approaching positive infinity. A couple more examples. Let's take a look at an example here. Let me go back. Here we go. First of all, notice that x is approaching negative infinity. If we look at our most dominant powers, we have 5x squared and 9x. The powers for each of these are 1. So what that tells us is that we have equal powers. So we want to look at the ratio of the coefficients. If I were to plug in something like -1,000 for x, this -2, this +4, it's not going to have much of an effect. All right, but 5 times it versus 9 times it, well, think of it as these x's would divide each other out. You're just going to be left with the ratio of the coefficients. So this function would be approaching a height of 5/9. Okay, so the ratio of the coefficients just means the numbers in front. Okay, our next one here. This is a situation where, well, again, x is approaching infinity. This is bottom heavy because we have x cubed versus x squared. Okay, the 3 outweighs the 2. So we call this bottom heavy. We don't care about this +6x or that +3. All right, it's not going to have much of an effect on things if we plug in something very large for x, like 1,000. Now, it's bottom heavy because if I plug 1,000 in up top, square it, and then multiply it by 50,000, versus putting 1,000 into the bottom and cubing it, there's more weight in the bottom. You'd be dividing by a much bigger number than you have up top. So this is a really easy type of limit question because the answer is always going to be 0. Okay? If you divide by something bigger, it's going to approach 0. And finally, we have a couple trig examples here. We have a special limit here. The limit of the sine of x over x as x approaches 0, by definition, is going to equal 1. Now, what this is suggesting is that you have to have the same expression here, right? This angle has to match what you have in your denominator. If that's the case, the limit will be 1. And you can easily graph this to confirm that it's equal to 1. In our first example here, notice that we have the sine of 3x over x as x approaches 0. Notice that we have a mismatch. That's a 3x and this is an x in the bottom. We have to make these equal in order for this rule to apply. So if we were to put a 3 down here, okay, I could balance this out by multiplying the numerator by 3. So technically I'm not changing the problem at all. Okay, because 3 divided by 3 would just be 1. We're multiplying by 1, so it's not changing anything. So this piece right here, okay, the 3x, the sine of 3x over 3x, with the limit as x approaches 0, that's just going to give us 1. Times, we're left with that 3 up above, that's going to give us a final answer of 3 for our limit. So be on the lookout for problems like this where you can have the same expression with the sine function as x approaches 0. All right, that'll give us 1 for that part of it. The last one here is an example where we're looking at a couple different trig functions. What you want to do is keep your identities in mind. So if I rewrite this and carry over my limit notation, tangent, recall, is the sine of x over the cosine of x. And secant, we have an identity for that. That's 1 over cosine of x. And by the way, I should have mentioned earlier that if we were to plug in early on to each of these, you would have gotten 0 over 0. That should have been the first thing we did. Okay, so 0 over 0 suggests there is an answer out there. We just have to do some algebra to get it. In this first situation, we have a special rule to find it. Down here, we're looking at some identities to find the answer. Well, if we rewrite this, sine of x over the cosine of x, dividing by 1 over cosine is the same as multiplying by the reciprocal, which would just be cosine. So notice the cosine of x terms will cancel each other out, leaving us with the limit of just the sine of x as x approaches 0. Got my 0 there. So we would simply do our direct substitution now. We would have the sine of 0, which is 0. Okay, so here we're not using this special case rule from up above. Okay, it's a different type of trig limit question. Here I'm trying to show you that you want to keep in mind your identities. All right, identities make life a lot easier because quite often, as you'll see, things will cancel out and then you're left with something fairly simple to plug in and get your value.